good results, which are good enough for a prototype, and they also run fast enough so that you can actually test the features that we will want to build on that environmental understanding. And to give you a very rough idea how that works internally, so you understand all the ideas later on, is basically what we do is, I'm going to explain it here on one single input depth image, is we first rasterize the input depth image into a group of superpixels, where each superpixel represents another group of pixels. We then take those superpixels and compute the normal on top of that plane using a technique called PCA, or principal component analysis. And then we try to find all the planes which are within that input image by using a region-based, region-growing based approach, where we compute, like we use the normals and compute, like compare the like similarities of the normals within neighboring regions, and then in a final step, we then pick the ground that we are standing on. And the one thing that we realized, unfortunately a bit too late, but quite in the beginning, and that's what I want to, like that's why I'm stressing it so much here, is before you even start a single like minute into optimization, I think it's really, really important that you first find out what are the actual bottlenecks, what parts of your algorithm are slow, what parts are fast, so that you spend the time on the right things. And as you might have all know this example, which is Amdahl's law, where if you take an original process which consists of two parts, in this case A and B, and you decide by whatever reason to work on the actual faster part and improve it by a way bigger margin than what you could improve the slower part, the overall runtime won't be as good as the one where you worked on the right task. And when we think about it, okay, how can we do that in Python? A very initial idea would be, yeah, okay, why don't we just use the timed operator in Jupyter Notebooks, or we wrap our functions with time functions, but that is very, very tedious to implement on big projects and also doesn't give a really detailed feedback. So the idea would be that we use something that is already built in with Python, which is cProfile. It's a built-in profiling tool, as I mentioned, and it's very easy to use, and it allows us to measure the performance of each function. And if we wrap our code with cProfile, we get an output like this, which already gives us all the information that we need, but in a very unreadable and not really easy to understand format. So what I would always recommend is to use on top of cProfile would be a tool called SnakeVis. The idea here being that we can now take that data, visualize it nicely, and as we can see, by chance, the resulting, the biggest part, the planarity check and the region growing, actually are pretty similar to the example of Amdahl I gave at the beginning, and we can see that it might make a lot more sense to work on PCA, which is the biggest part of the planarity check, than on the actual region growing to see that we improve our code. The second step that we usually do at biped after we now found out what is slow and what is not, is to look at the algorithmic design or the underlying process. Instead of saying, hey, why don't we just improve the code directly, I think there are a lot of gains that we can actually get before improving code by just looking at the algorithm and seeing if there is something to improve. What we mean by this is, for example, are there approximations that we can make? Instead of doing a full computation, are there approximations that we can make that are easier to compute but give us like a similar result? Or is there, for example, the way that we can say, are there conditions that can simplify the process and then let us like not do the computations on edge cases? And in our case, for example, what this could be is PCA takes 65% of the total computation time. So why don't we compute, for example, PCA on a subset of the points in each superpixel? Or, I mean, as you've seen in the beginning, there are quite a few superpixels which are completely invalid, and it's easy to see that they're invalid. Why don't we just kick them out before? And so what I mean by sampling here is why don't we use why don't we uniformly sample over the input superpixel list of pixels, and then only use a subset of that. And what we see there is we can get very similar results while improving the computation quite a lot. And then when we kick out all the invalid superpixels with, for example, very simply to check conditions like, are there too many invalid depth pixels in black, for example, or is the depth variation within the superpixel super high, then we can further do a step and improve more on that. And just to summarize so you can follow along, I mean, what we have right now is we go over each superpixel, We then check the conditions that I just introduced. We then sample and then compute the normal on just the sampled output using PCA, which is then finally followed by the region growing and the selection of the ground plane. Now that we have found out, okay, this is slow, this is fast, we've also optimized our algorithm, we can go to the point where we optimize the code in itself. And there are two very obvious solutions to that. It's like one you will probably all know, it's NumPy. The idea here is if you have vector or matrix data and you want to work with that, what you will see is that Python naturally is quite slow with that, and there is obviously the thing that you use NumPy, which efficiently vectorizes operations, and one of the reasons why it's so fast is that it actually stores the data in continuous chunks of memories. And just to remind you all what kind of benefits are possible here, I've implemented a very simple function in normal Python, and then the same function would take a very small part of that time in with NumPy. The second option that we have is using Cython. The idea would be here that we take type annotated Python code and then compile that to efficiency code. And we use that efficiency code and then can import it very like normally how you would import other Python modules. And this is especially good to have if you are using loops, if you still have to use loops, or if you want to operate with a lot of mathematical operations. And one warning here is generally NumPy and Cython work very well together, but without type annotations, that in some cases can lead to some slowdown. So just to keep that in mind. And I have one small example here where we have a function within the whole pipeline where we convert coordinates from one coordinate system in the other. And if we implement that in Cython, and we can see that there's also some gains to be made. Okay, the next idea that I think naturally comes to your mind at one point is, until now, we've done all our operations in a sequential fashion. So the idea would be you do all the computations and you compute the PCA operation like for each superpixel one after another. But especially this is easily parallelizable. And so the idea that what everybody that I think has anything to do with computers comes to mind, hey, why don't we use multi-threading or multiprocessing to use that offered possibility of parallelized computation? And there's one thing that you have to keep in mind. Within Python, there is a problem with threads, the way Python is implemented, that threads are not really able to help us here due to a thing called the global interpreter lock. And the idea is that Python is implemented in a way that there is only one Python interpreter running on one process. And so the different threads which seem to be parallelized are actually not parallelized because only one of them can access the memory space of that interpreter at a time. And so you can't actually get the gains that you want from parallelizing. What we have to do instead is actually do multiprocessing instead of multithreading, because here we have different Python interpreters with their different memory spaces, and so you can actually get the gains from a system that has multiple CPUs or cores. So just to summarize that, multiprocessing for CPU-heavy tasks, multithreading for I/O-intensive tasks. One thing to keep in mind, though, here is before Python 3.8, the most common way to communicate between different processes was with something like a queue. And the problem here is that when you use queues, there is actually some copy operations under the hood that are needed. And just to symbolize that here, I've created a little example where when you use a queue to copy big image data, if you just pass around strings, queues can actually be fine, but if you use big image data, like in our case, where we, for example, pass 1,000 times 3 images of a size 1,000 by 1,000, you see that only the copy operations between two processes actually take up to over 5 seconds. And that's, I guess, one of the reasons why in Python 3.8, a module was introduced that allows us to allocate and manage shared memory and pass those references to these memory between different processes. And you can see if we switch just for the communication between a queue-based approach to a shared memory approach, we can have gigantic gains in performance. Here, you can see one of the bit older examples of what this brings us. So obviously, it's not everything is perfect, but we can see here the pipeline is actually fast enough to take some of the ideas we had, which is, for example, on the right, a very basic understanding of what is happening around the person, And within that system, we have our underlying floor segmentation, which now runs fast enough due to all the different steps we've taken so far. If I summarize here, is the question first is, am I using the right hardware? And then the biggest, like the thing that I would say the most is, I mean, the 3 steps are basically profile what you do, visualize and track your performance, then improve the algorithm before everything else, and then I would say before you try to optimize something and implement something yourself, see if there is a library for it, because they most have likely done it better than you. Okay, and similar to the sound sensing guys, we are also a small startup that is still growing. We are based here in Lausanne, and we're also looking for people. So if you're interested in working on making the lives of blind and visually impaired people a bit easier, then yeah, we're very happy to, like if you get in contact with us. Thank you very much for listening.